today what we'll be doing is we'll be going over the information that we need in order to perform the lab, okay? So that'll be what are the properties of ionic compounds, of molecular compounds, what are some physical properties of certain types of elements and groups and things like that, because that'll help us in our lab where, again, we will have a dozen unknown compounds at the front of the room, okay? You are going to perform various tests to determine those compounds' physical properties. And then you will use the physical properties for each unknown in order to discover its identity. So the information in today's lesson will be that stuff that will let you figure out whether the thing that's blue is ionic or molecular, and whether it's an acid or a base, and whether it's copper sulfate or water. Okay, those kinds of things are what you're going to get from today. So you'll want to probably highlight a few things as we go along, or make a few notes, because I do tend to drop big juicy hints for helping you with the lab report analysis when I'm teaching this lesson. Right, so you want to be watching for that stuff. Okay, so the key points for today: learn the properties of compounds, acids, bases, ionic, molecular, okay, and understand how these properties can be used to identify a compound useful for your lab. Okay, questions so far? Okay, so compounds. If we think back to Dalton's atomic theory, he said that compounds can occur when elements join together in whole number ratios. Okay, so that's what we're going to be looking at. We're going to be looking at fairly simple ionic and molecular compounds in our lab. Okay, all matter has certain properties. Some of them are physical properties. Okay, and you probably learned about the difference between physical and chemical properties last year, but just quick review. Physical properties are things that are observable and measurable with only that material available to you. Okay, so that would be things like melting point, boiling point, state, color, odor, okay, those kind of things that you could observe if you just had a chunk of that material. Chemical properties are not evident until the material reacts with something else. Okay, like for example, if I had never encountered gasoline before, okay, if I'd never seen this stuff, had no idea what it was or what its uses were, okay, would I know that it could catch on fire or explode just by looking at it? No. Okay, because that's a chemical property. I don't know that this stuff is highly reactive with oxygen until I find out, which might be bad. Okay, so I can't tell if something has certain chemical properties until I see them in action, and that requires whatever it's going to react with to be present. Okay, so our lab will basically be only dealing with physical properties. We're not going to be doing any reaction stuff in this lab. That'll be our next lab. In our next lab, we'll be mixing all kinds of things together, okay, and looking at chemical properties and reactions and things of that nature. Okay, so these properties can obviously be used to distinguish between different types of compounds. So we've got things here like color, density, melting point, etc. Okay, some other big ones: solubility. That's a very important physical property. Okay, what is solubility? Anybody know?
Dissolve in water or liquid.
Right, its ability to dissolve in something else. Okay, most of the time we refer to solubility as ability to dissolve in water. Okay, but it's not strictly that way.
Are the solubility in our lab all in liquids, or are they solids?
No, you have many that are solids. You have 2 liquids, and you'll have 1 compound that is already in solution, because we can't get it as solid. Yeah. So that's what you have. Mostly solids, 2 liquids, and 1 thing that's already in solution. Okay, so solubility, that's a pretty important one. And going along with solubility, okay, is the ability to conduct electricity when aqueous, or when in solution. Okay, and we'll talk about that here in a little bit. But solubility is one of the biggest ones. But we have a lot of properties that are just simply observable. That would be things like color. Okay, that's just a strictly observable property. I look at it, it's white, it's blue, it's green, whatever. Okay, melting point's not something we're going to do, because a lot of our compounds are ionic, and ionic compounds have a very, very high melting point, several hundred degrees. We're not doing that. Okay, so we won't be measuring melting points. However, if you get something that's a liquid at room temperature, it's probably not what kind of compound? Ionic. Okay? The only way an ionic compound would be a liquid is if it was several hundred degrees Celsius. So if I get something that's a liquid, I know it's not anything on my list that's ionic. It has to be something molecular. Okay? All right. Other things like butter, for example. Butter is a molecular compound. Coconut oil is a molecular compound. You put those things in your hand and they start to melt. They have low melting points, whereas ionic compounds have very high melting points. Things like that. All right. So, ionic compounds. Now we talked briefly about ionic compounds properties, but mostly in terms of their bonds and how their bonds work. And what we're going to look at today is some of the more observable, testable, detectable types of properties. Okay, so first off, they typically exist as crystalline solids, known as salts, at room temperature. Okay, because they have very high melting points. Okay, and ionic compounds will conduct electricity without exception. Okay, there are no exceptions to this rule. All ionic compounds will conduct electricity when in solution. Okay? Whoa. That's not where I pushed. So, the big thing here with ionic compounds conducting electricity in solution is because of what we talked about earlier when we talked about how they bond together. Remember we said their bonds are very weak and they trade their electrons. So when you dissolve them in water, they split. Okay? Well, what happens when they split is you end up with charged particles called ions, hence the name ionic compounds. Okay? So if I have sodium and chlorine, okay, sodium chloride, when this thing splits, I get Na plus and Cl minus, because chlorine takes the electron that sodium gives away. Well now, floating around in this solution are little charged particles, positive sodiums and negative chlorines. When you have that, electricity will flow through the solution. If you don't have charged particles in a solution, electricity won't flow through it. So if I have just plain distilled water, it will not conduct electricity because there are no charged compound or charged particles in it. Okay? If I make a solution of distilled water and sugar, will it conduct electricity? Nope. Because sugar is molecular. It's made of carbon, hydrogen, and oxygen. Okay? It doesn't break into charged particles because it's not an ionic compound. Right? I think we used this example, but pool water, okay, would conduct electricity because it's got lots of ions in it. Okay? Hypochlorite and things like that, the stuff that smells like bleach in a swimming pool, the chlorine. Okay? That stuff would help that water to conduct electricity. So when you're running your tests in the lab on Thursday, one of your first tests will be a solubility test. And then, after that, you will check the conductivity of those solutions. If they conduct electricity, that compound is ionic, without exception. Okay? That is your one test that will always tell you, this one's ionic, this one's not. Okay? It will always tell you that. Right? We have little conductivity testers, okay, that give the conductivity on a scale of 0 to 10. Okay? Basically anything below 4 would be molecular, and anything else, okay, would be ionic. But there's basically nothing. I don't think there'll be any compounds that will give you a reading between 2 and like 7. Okay? They'll either be like virtually non-conductive, or they'll be higher than 7 to 10. Okay? It would be pretty obvious. If you get some reading in between, probably something went wrong. Okay? Try it again. Okay, so does that make sense? Okay, so that conductivity test, okay, is going to be pretty important. So we'll just make a note here, conductivity test. Okay, reveals ionic versus molecular. Okay. Now, typically, ionic compounds are highly soluble in water. Typically. Doesn't always mean they're highly soluble. There are some things that are not. Okay? But molecular compounds tend to be less soluble. So if I have like sugar and salt side by side, okay, they look very much alike, okay? And they're both pretty soluble in water, but salt would be more soluble than sugar would be, okay? Just because sugar is molecular. Okay? All right, a couple of other things, colors, okay? There are some metals that make ionic compounds that are brightly colored. Nickel is one of those metals, okay? Nickel always makes green crystals. So if you have a green crystalline solid that conducts electricity and is highly soluble in water, it's probably an ionic compound containing nickel. Right? So it's something to watch for. Okay, so green is indicative of nickel. And there are exceptions, but like 99% of the time. Okay, so many ionic compounds produce solutions that are brightly colored. Copper compounds will always be blue. All right, so if you have a blue crystalline solid, then it likely contains copper, especially if that dissolves in water, conducts electricity, et cetera, et cetera. And another one is cobalt. Okay, cobalt typically makes pink or red. Okay, and their solutions obviously retain that color. So when you dissolve the blue crystals, the solution turns blue. When you dissolve the green crystals, it turns green, etc. Okay, so those ones are really, really useful when it comes time to go, okay, I have compound C, which is a red crystalline solid, conducts electricity, blah, blah, blah. That's probably this one, because this one contains cobalt, and be done with it. So you get a few kind of freebies, okay, when you're doing your identifications because of these obvious colors. Okay, questions on those? Yeah, properties of molecular compounds. If we're looking at ionic versus molecular compounds, okay, ionic would be here. They are charged particles together in pairs, and they typically orient this way, which is why we typically get organized crystalline type structures. Okay? Molecular compounds, on the other hand, because they have no charges, don't align in any way. They just kind of randomly fit together, which is why typically as solids, we don't get crystalline shape for molecular compounds. They tend to be softer, waxier, okay, things like that. Okay, less kind of hard. Okay, typically. Obviously, there are exceptions like sugar. Okay, is a crystalline solid, but it's not very hard. The crystals aren't very hard. Okay, ice. Okay, another one. Okay, water's molecular. Okay, and ice is crystalline. Snowflakes are crystalline. Okay? But no two snowflakes are the same. Okay? Whereas the crystal, you can actually identify ionic compounds from the shape of their crystals if you're looking at them through a microscope. Okay? They'll always be the same. So. All right. So molecular compounds can be solids, liquids, or gases at room temperature. We talked about that already. Okay? You know that the two samples you have that are liquids are not ionic because ionic compounds are all solids. Okay? We don't have any gases, by the way, to test. Because it's kind of hard to contain them in a beaker. Right? You could test air, but it's really hard to test all the tests we want to test on here. Okay? Like you say, they tend to have low melting and boiling points. Okay? Like for example, water, right? It's got its melting point is 0, its boiling point is 100. Those are pretty low. Okay? Butter melts at about 40 degrees. Okay? Coconut oil at about 30, okay, something like that. Like on a hot day, if you leave it out on the counter, it turns to liquid. Okay, and so stuff like that. Very low melting and boiling points. Okay, and their solutions do not conduct electricity. So molecular compounds are not usually as soluble. Okay, and the solutions they form do not conduct electricity. Another thing about molecular compounds is they don't tend to have extreme pHs. Okay? So molecular compounds don't tend to be strong acids or strong bases. They tend to be kind of more in the middle. Okay? reason for that has to do with how acids and bases work, which is what we're going to talk about here right away. Okay? Strong acids and strong bases are ionic compounds that give off hydrogen and hydroxide, the ions associated with being acidic or basic, whereas molecular compounds can't give off ions because they don't have them, so they're typically less strong. Like, for example, citric acid. Okay? Citric acid is an organic acid. It's not strong. Okay? It's not going to eat away at your skin. Right? It's in citrus fruit and that's it. Whereas hydrochloric acid is very strong. It's an ionic compound. All right. Questions on that? Okay. Molecular compounds that are soluble in water will produce clear solutions. Okay, and like I said, there are some that are quite soluble and there are some that are highly insoluble. Okay, there's not really a general rule for molecular compounds. Okay, but if you dissolve sugar in water, I mean, it gets a little bit cloudy, but it's not colored. Okay, same with alcohol. Okay, if you put alcohol in water, it just dissolves. Okay, it just mixes in. Okay, it is possible for one liquid to dissolve in another liquid. Okay, and we do that all the time. Okay, so if you mix you pour just rubbing alcohol into water, it just mixes right in. Okay? Whereas if you pour like melted coconut oil into water, it separates. Right? That's insoluble versus soluble. Okay? So when you're running the solubility test, that's one of the things you want to look for when you're testing the liquids. Does it sit on the top or does it mix right in? Okay? If it mixes right in, it's not sitting on the top layered, then it definitely is soluble. Okay. Acids and bases. All right. Something can be a strong acid if it has hydrogen acting as the metal. Okay? The presence of the H+ ion is what makes something acidic. So if I put a strong acid into water in its solid form, which typically we don't get, okay? It's really dangerous to keep them in their solid crystalline form, okay? If I put that and dissolve it in water, it will split into the H+ ion and whatever it was with. In the case of hydrochloric acid, that would be that, because hydrochloric acid is just HCl. When I put it in water, it splits into H+ and Cl-. Will that solution conduct electricity? Yes, and it will conduct it very well. Okay? Your strong acids and strong bases are going to be also your best conductors of electricity because they dissociate the most easily. Okay? They're the ones that don't stay together. Okay? Some ionic compounds stay together better than others, but acids and bases split right away. Okay? They dissociate very quickly. Right? So the more H+ that an acid can donate to a solution, the more acidic it will be. Okay? That's why the more concentrated an acid solution is, the more acidic it is, because the more H+ it will have in it. Right? So which would be a stronger acid? HCl or H2SO4? H2SO4. It's got more H+ ions to donate to the solution. Okay? When this goes into solution, I'm going to get H+, and SO4 2- in solution. Okay? It's going to donate twice as many H+ ions as an equal amount of hydrogen chloride. Where do we find hydrogen chloride? In your stomach. That's stomach acid. Okay? Your body can actually make and secrete this stuff into your stomach. Okay? Anybody know someone with an ulcer? Okay? An ulcer means that your stomach acids are actually eating your stomach. Right? Normally, your stomach secretes a lining made of mucus, snot. Okay? So there's like this snot lining around the inside of your stomach that protects it from the stomach acid. That way the stomach acid can work on your food. It helps to break the bonds and proteins and things like that. Okay? But it protects your stomach from the acids because it's always secreting this lining. Certain things in your diet and certain kind of behaviors can cause that lining to not be secreted properly or to thin and allow the stomach acids to burn the inside of the stomach. People with lots of anxiety, okay, they're very like basically kind of like, to the point of kind of mental illness, anxious, okay, they will often develop ulcers because anxiety and adrenaline tends to limit the production of the stomach lining, okay, and so they're more likely to develop ulcers. Alcoholics are also likely to develop ulcers because consuming a lot of alcohol breaks down the mucus lining, okay, and allows the stomach acid access to the stomach lining, the inside of the stomach. Anytime you get heartburn, and people have had heartburn before, okay, that's the stomach acid coming up past the stomach, okay, gets out of the stomach and into the esophagus. The esophagus doesn't have that mucus lining, okay, and so you actually feel burning around your heart, but it's actually your esophagus being slightly burned, not enough to ulcerate it, but okay, slightly burned by your stomach acids. If you vomit, okay, you know, it feels like it's burning all, yeah, that's stomach acid, it's burning, okay. Incidentally, that's also why after you throw up, you should brush your teeth, okay, because the acids will eat the enamel on your teeth. It's another thing that happens to alcoholics. Okay? If they drink heavily and are often throwing up, their teeth will often rot, okay, because the stomach acids will start to decay their teeth. Okay? Don't drink, it's bad. Okay? All kinds of ulcers and rotten teeth, while all those other bad things that go along with that. Okay? So yeah, just be aware, okay, acids, okay, they can break things down because they're going to break into these ions. These ions can cause reactions to happen because now they're available to react with other things. That's a chemical property, but that's what goes on. Okay, so acids have H plus ions in them. So any unknown with hydrogen listed first as a metal is likely to be a acid, a strong acid, okay, a strong acid. So acids are, like we said, ionic compounds, so they're going to conduct electricity. This is one that will not apply to our lab. Okay? I am sure that hydrochloric acid tastes very sour, but I'm not going to try it. Okay? Because it'll be the last thing I taste. Like the last thing I taste to taste good. Okay? That's not going to be it. All right? You don't want to taste test anything, especially since I made everything very, very concentrated. I made the solutions up on Friday. Okay? That one actually smoked a little bit when I made it, so it's good. Okay? Really, really good. Yeah, that happens when you add acids to water. You always add acid to water. No, I didn't say taste it. Okay? I said it smoked a little bit when I made it. Okay? You never add water to acid because when you mix acid and water, they get hot. Okay? The temperature goes up. There's a bit of a chemical reaction that goes on there. Okay? And the temperature increases. Water has a high heat capacity, which means it can absorb a lot of that energy from the reaction. If you go the other way, and you're adding a small amount of water to a large amount of acid, it'll heat up so much that the glass will expand too quickly and break. Okay, so you never add acid to water. Or sorry, you always add acid to water, never the other way around. Okay, and when I added the acid to the water, little wisps came up from it, so it's good. Okay, just be aware though that obviously it's quite concentrated. We don't know which one's which, so be careful with everything. Okay, no taste tests. Okay. We will be using not the simple red and blue litmus, okay? We're going to be using the Hydrion paper, which has 14 different colors, okay, that it changes into, and there's a little color chart on the cover, okay? So you're going to get a little tube. I'll bring one in a little bit, okay? It's a little plastic tube, and inside the plastic tube is a color card, okay, that tells you, red is 1, basically bluish black is 14, and there's a bunch of colors in the middle. Okay? So that's what we'll be looking at, okay, to do our pH test, because the pH test will be one of our tests. And obviously it'll tell us which thing is very strong acid and which thing is a very strong base. Okay? All right. Now, bases, strong bases that is, okay, are also ionic compounds, and their solutions will conduct electricity. Again, they'll be one of your best conductors. Okay? Typically, bases taste bitter. Again, not something you're going to try, but if you've ever had your mouth washed out with soap, soap is a base. It contains lye. Okay? Lye is a base and it tastes bitter. Right? And they'll turn the litmus indicators basic colors, typically bluish black. Okay? Bases always have OH minus ion, that is hydroxide. It's a polyatomic ion, but it is present in all strong bases. Right? So the other day I was telling you about the stuff that's in oven cleaner. Okay? It's a very strong base, which is why it can eat away the crud inside your oven. Right? It's also why it burns if you inhale the vapors. That's why you're supposed to, when you use it, you close the oven door, you turn on your oven fan, you open doors, okay, windows, things like that. You don't want the vapors. You don't want to inhale the vapors. Okay? All right, so this stuff, when I put it in solution, breaks up into Na plus, OH minus, okay, and the presence of the OH minus, okay, makes something basic. Right? So if you're looking at your unknowns and you see an ionic compound that ends in OH, that one's likely to be a base. Okay. Now, what if I saw this? Would that be a strong base? No. Okay. Why is that not a strong base? Well, it's got hydrogen in it and hydroxide, but it's what kind of compound? It's molecular, right? It starts with carbon. Okay? It doesn't start with a metal. So even though it looks like it should be a base because it ends in OH, it's not. In fact, this is alcohol. Okay? This is the formula for ethyl alcohol. Okay? C2H5OH. It's not a base. Okay? In fact, it's got a pH of about 6. If anything, it's a very, 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 very weak acid. All right, so not something, okay, that's going to be a base because it's not going to break up when I put it in water. Okay, this isn't going to break up into charged particles, so it won't create a basic solution. So something to watch for because it can be misleading. All right, so basic solutions have a pH that's higher than 7. Acidic solutions obviously have a pH that's less than 7. We don't generally consider something to be a cause for concern unless it's significantly higher or lower than 7. Okay, like we don't even consider rain to be acidic, like acid rain, until it has a pH of less than 4. Right? Because actually most rain is like 5, okay, 5 or 6. Okay. Acid rain is obviously worse than that. Okay. Questions on that? All right. So those are some of the things that we need to know. Okay. Now, in terms of tests for your lab, okay, that's what we kind of want to go over next here. Is what kind of things do we need to be looking at for the lab? Okay. The first thing we want to do, and this you're going to need to write down, okay, because it's going to be part of your procedure. Okay, the first test that you're going to run on your unknown compounds is what we're going to call the observable properties test. Okay. Observable properties are just like it sounds. The things that you can see or observe directly just from having the sample in front of you. Right? So those would be things like color.
Are we going to be sniffing it?
Yes, you will be wafting things for odor. Okay, so color, obviously you're just using your sight for that one. Okay, odor. Okay, that you'll be wafting. And my suggestion would be to waft the original samples. Okay, because what you're going to get, and I'll show you all this stuff here in a few minutes, is you're going to get a depression plate. It's not sad. It's not depressed. It has depressions in it. Okay? If you have a contact case, it looks like it has room for like a dozen contact lenses in it. Okay? Looks like this. Okay? Each one of these is a little pit or depression. Okay? It's not funny. Okay? You shouldn't joke about mental illness. It's not funny. Okay? Correct. So you're going to have this depression plate. If you put, and you're going to put all the samples in there, and my suggestion would be is when you do this lab, you're going to label them all with a permanent marker, and then we'll take them off with alcohol after. Okay? So you just label each one, put sample A in depression A, okay, and so on and so on. If you're trying to waft these samples, you're smelling them all at the same time, okay? You're not gonna do an effective job of it. So I would waft the original samples, and is that something you should include in your procedure? Yeah, remember we said you gotta make it so like the dumbest person you know can follow it? Okay, so I can follow it? Okay. That's what you're looking for. So odor test, okay, that's gonna be part of the observable properties test, okay? State. Okay, so solid, liquid, or gas. Obviously, there won't be any gases. Okay, this one will also be important, whether it is aqueous or not. Okay, that means it's already dissolved in water, and there is one that you'll have that's already dissolved in water. Okay, nature. What I mean by nature is it, if it's a solid, is it crystalline, waxy, non-crystalline, okay, etc. Just the nature of the solid. Okay, so basically those are the things that we're going to be looking for. So when you are describing how to do the observable properties test in your procedure, these are things that you want to explain, right? So, you know, it'll probably be like step 3, but perform the observable properties test by A, recording the color of the compound, B, okay, wafting the original sample and noting any strong odors, okay, C, looking at the state, is it solid, liquid, or gas? Looking at the nature of the material, is it crystalline, waxy? Record all of these pieces of information.
How would you want us to describe odor? Like, you can't just say it smells bad.
Well, you could say like strong odor and compare it to something.
Okay.
Okay, like for example, one of your unknowns is ethyl alcohol. Does alcohol have a pretty distinct odor?
Yes.
Yeah. Okay. Most acids tend to smell kind of like vinegar. Okay, they have that kind of burning kind of smell. Like when you smell them, right, you feel like the nose hairs curl. Okay, like kind of like that, right? So like that, but really strong vinegar. Those to just record what you think it smells like. Okay, I mean, if you come with, like water is one of your unknown compounds. You're holding a liquid going like this, it doesn't smell like anything. You say it doesn't smell. Okay, don't try and make stuff up. If it's not a smell you recognize or it's not very strong, don't note it. Okay, we don't want it to throw off our identification. All right, there's only basically 2 things where the odor is really important. Okay, the other ones basically don't have a smell. Or if they do, it's not important. All right, so that's your observable properties test. The next test you're going to want to run is your solubility test. Okay, when you're getting the samples, is it important to know how much of the sample to put in?
Yeah.
Okay, you're going to want to record this. You're going to want to fill your sample depression about, let's say, 1/3 of the way full. Okay, so not much. You don't need much of any of these compounds. 1/3 of the way up is lots. Okay, more than half, and you'll never get it to dissolve effectively in the solubility test. It's going to spill more easily. It's just a pain in the neck. Okay, so what we're looking for, okay, is to put in about 1/3 of the way full with the original material. For liquids, you could add a little bit more, but for solids, 1/3 of the way. Okay, in the solubility test, you're going to add what? You're going to add water. Okay, so when you're running the solubility test, okay, fill depression to 3/4 full. Do not fill it all the way, because you're going to need to have a thermometer in there while you're doing this test. And the next test, you're going to need the conductivity tester in there. If you fill them full and then put in something else, it will displace enough water equal to its volume and it will spill. Okay, so 3/4 full. Okay, with thermometer in place. Okay, so put the thermometer in, then add the water. Some of these will have temperature changes, but because we're dealing with such small amounts of everything, you need to have the thermometer in there to get it right away. Okay? The ones that do change will be obvious. Okay? They will be several degrees. And there will only be really 3. Okay? There'll be 3 of these that will make temperature changes. 2 will get hotter, 1 will get colder. Okay? That's one to watch for. Okay, third test, conductivity test. Okay, while you're writing that down, I'm going to run across and grab some of these things so you can see what I mean. Okay, so some of the materials that you will get in the lab. Okay, this is the depression plate, right? I've already got a little bit of like salt in one of the depressions, about the same amount you would use. Okay, about 1/3 of the way full. I know it's hard, but if I tip it anymore, it won't. Okay, so about 1/3 of the way full. Okay, this is a thermometer. You probably call it a thermometer, okay? But it measures temperature. Some of them have this handy little red plastic thing on the top. Okay, that is so that your fingers don't interfere with the temperature reading. Okay, these things are accurate enough that if you're holding onto it like this really, really tightly, you'll warm up the alcohol inside and cause the temperature to change. So if yours doesn't have one of those, then I would suggest holding it as much as possible by the very top. Okay, so that you don't. But do be careful not to drop them. They break easily and they smell really bad. Okay, the methyl alcohol inside smells awful and stains the floor. So yeah, just be aware of that. Okay, so you'll have a thermometer, obviously. Okay, you'll have, this is the conductivity tester. Right, it's just got a scale from 1 to 10 on it. Okay, you'll know it's working when you press the button. The on light comes on. Okay, well, you say that, you act like that, but the old ones we had, you didn't know. If the battery was dead, you pressed the button, stuck it in. All you were waiting for was to see how fast the light, and one light would flash. The battery was dead, you got that it didn't conduct electricity, except of course it didn't, there was no electricity. And so these are better. They tell you I'm working and it doesn't conduct electricity. Okay? Then you've got your pH paper. Okay, and you can see here it's got a color chart on there. Okay, you just put the pH paper in the solution, and then I'll show you this in a minute. Then you stick it on here and kind of compare to judge colors. Right? Okay, and then you will also have a wash bottle. Okay, the wash bottle is for obviously doing the solubility test, but it's also for when you're done the lab, you'll take your depression plate to the waste bucket and spray it off into the waste bucket, getting everything to fall in there. It is not a squirt gun. Okay? If I catch you doing that, that is horsing around in the lab, and you will be back here, not doing the lab, watching me do the lab on YouTube instead. Okay? Which is really, really boring. Okay? You don't want to have to do it that way. All right, so if I'm doing all these tests, okay, so the first thing I would do, okay, is I'm looking at my observable properties test. I've got a white crystalline solid. Okay, the crystals, are fairly square but quite small. I've spilled some, so I would need to make sure that I cleaned them out of the other depressions. Okay, because I don't want to contaminate my other ones.
Would that be human errors as well?
No, you're going to know that. Okay, if you spill, clean it out. Okay, so I'm looking at that. There's no discernible odor. And that's about all I can say for observable properties for this one. Okay, the nature is obviously that it is crystalline. So if I'm doing the solubility test, okay, then I'm going to have the thermometer in the sample to start with, giving me kind of an initial temperature reading. Okay, these will all be the same temperature because they'll have been sitting in the lab. Okay, so they'll be the same temperature as everything else. And then I'm just going to slowly add it, squeeze it gently, okay, until it's about 3/4 of the way full. And okay, if you're going to stir, just stir very gently, okay, because these are not really designed for stirring. Just stir gently. Right? Obviously, the solution kind of got cloudy, and that would indicate that there's probably some dissolving going on. But I can also see that the crystals have shrunk. Okay? There's less of them now, and the crystals that remain are smaller, which would indicate that this is, fairly soluble, right? And quite soluble, in fact. If you're getting a significant change to happen in that volume of water, it's highly soluble. If it floats to the top, it's not soluble. Okay, but you will definitely see shrinking of the materials, okay, as it goes along. All right. Okay, so no temperature change, so I would record that as well. Okay, and then I would move on to my conductivity test. All right, so for the conductivity test, I take the conductivity tester, okay, I press the button, and I place it in the solution. Okay, and I have to be kind of patient with it because I didn't give it a whole lot of time to dissolve. Okay, but if I left this for longer, this is what you will do, because you'll do the solubility test for all of them, and then come back and start at the beginning again, okay, and do a good job of stirring. And if I do a decent job of stirring there, okay, then I'm going to get up to 7, 6, 7, somewhere in there. Okay, so is that conductive? Yes. Okay, so this stuff is, it's ionic. I mean, we know that it's salt, so it's ionic. Okay, that makes sense on how that one works?
Oh, yes.
Okay, so that's a pretty easy test. What should you do between tests to both the thermometer and the conductivity tester? No. Why am I rinsing it with distilled water? It doesn't have any ions in it, right? Can't interfere with my tests. Don't rinse this under the sink. Okay, there's ions in tap water, right? So give it a rinse, and then, I mean, if you want to, you can use a piece of paper towel, but I would just give it a little shake, and you're ready to go to the next one. Because could the paper towel put stuff on there?
Yes.
Perhaps, okay? So we want to eliminate that as a possibility. Okay, last test that you're going to do, we don't have it on the board yet, is the pH test. So we're not running a whole lot of tests. And yes, the P is supposed to be lowercase, stands for power of hydrogen. Okay. All right, so that'll be litmus paper. Ooh, I spelled color the other way. Okay, and then use the color chart to determine the pH. Now, the thing with the Hydrion paper, okay, so when you open up the vial, you'll either have one or two of these. Okay, one piece of the pH paper should test 2 samples. Okay, so you can either tear it in half, or I would suggest tearing it in half, because if you use opposite ends, you're going to put your finger on the sample from the first end. Okay, so just take that and place it in the solution. Right, it'll change. The color change is pretty much immediate. Right, so this, I'd say probably closer to 6. It's definitely not a 7. Okay, so probably a 6. I'd say that's closer to 6 than it is to 5. Okay, again, if you're within a couple, basically there's only really 2 that'll have a big reading one way or the other. Okay, and those 2 are really important because they help you to identify the 2 compounds. Okay, they're involved. All right, is that making sense to everybody? Okay, so that's kind of how that'll work. Okay, and I just kind of show you that so that today, if you get to your procedure design, you kind of know what things to tell the person who's following your procedure. All right.